It's a pleasure to have today Kaixing Cao from Unimi to talk us about the truncated cases for Tannaka duality. So please, Kaixing.
Okay, thank you, Finn. Today I will talk about the truncated case of the Tannaka duality for geometric stacks. My talk will divide it into two parts. The first part is record some Tannaka duality for geometric stacks discussed before, and then we introduce or record the truncation of the geometric stacks, or even more generally, we can talk about the truncation of the quasi-geometric stacks. And then we give the statements of the different version of the Tannaka duality in the truncated case. So first, let's recall our Tannaka duality for the geometric stacks. It tells us if we giving a geometric stack like x, then for arbitrary function y from the connected infinite ring to the anima or to the infinite category of spaces, the y point of x is there is a unifiable embedding of the y point of x to the functor category, which is consists of the symmetric monoid functor from the constant core of x to constant core of y. And, and we can even describe this essential image, which are generated, which is a first of category generated by preserving the small coordinates, connective objects, and flat objects. So it means that for geometric stacks, we can recover the quotient core, this category of itself. And here we need when we somehow this shows that the y point of x is equivalent to this full subcategory, and we require that this symmetric monoid functors lying the essential image preserves the flat objects. But when x has some finite is under some finite conditions, like x is perfect or locally non-theory. But here we even talk about the constant geometric stack, which having the finite condition, we can drop the preserving the flat object is automatic. But today, the flat objects will play a very important role in today's talk. And because we need to pass to the truncated case of the Tannaka duality, we need to know what the truncation of the quasi-geometric stack or geometry stacks. So for quasi-geometric stack X, and if we are giving a natural number, if we can find the 5 fully flat morphism from the affine space, which is associated to from the untruncated commutative ring of spectral, then we see X is truncated. The first one is an equivalent description for the truncated quasi-geometry stack. So it means that from this definition, you can see we require that we have the 5 flat morphism from a affine space associated to an untruncated case. It means that the quotient core of X has a nature of untruncated property. Now, because every quasi-geometric stack is a functor from connective in infinite rings to the anima. So we use this to denote the full the infinite category of the constant geometry stack. The QG is a constant geometry. And now we have the notion of the untruncated constant geometry stack. We also use this notation to denote the infinite category of the untruncated constant geometric stacks. So one can see that we have the including functor from the untruncated constant geometric stack to the order to the infinite category of all the constant geometry stacks. And this inclusion admits a right adjoint. So we know that the untruncated constant geometry stacks is the co-reflective subcategory of the category of all the constant geometry stacks. And the co-reflector is a right adjoint of the including functor, will be denoted by the standard notation, the standard truncated notation. So hopefully because we have seen by the definition, a constant geometry stack is just a functor detecting by all the connected commutative algebra spectra. But for the untruncated constant geometry stack, we hope that we can only detect all the untruncated connected commutative algebra spectra. This is this proposition proved by Lurie. It means that because firstly, every constant geometric stack which is untruncated is the full subcategory of this functor category. And this is a restriction function induced by the inclusion from the truncated algebras to all the algebras. And this proposition tells us that the composite functor is fully feasible. So in particular, we know for truncated constant geometry stack, we don't need to detect by all the connected commutative algebra spectra. Instead, we only need to detect it by untruncated ones. So because we can take n is a 0, then we get the discrete or zero truncated constant geometry stacks. And it's completely determined by the discrete commutative algebras. So this links to the classical algebraic geometry. So whenever we have the truncated version of the Tannaka duality, in the view of this proposition, we can somehow, if we take the zero truncated case, we get the a kind of version of the Tannaka duality for the classical algebraic geometry, because it's just detected by the ordinary commutative rings. Now let's consider our truncated version of the Tannaka duality. We firstly start from the discrete case, because in the discrete case, maybe we recall that for we may only consider the geometric stacks. For the geometric stacks, the y point of it is the same thing as the functor category, the full subcategory of the functor category between the crossing from x to y, generated by those preserving the small coordinates, connected objects, and flat objects. Now, in our discrete truncated Tannaka duality, we use the heart of the I mean in the original version of the Tannaka duality for geometric stack, we describe the essential image by one of the condition is preserving the collected objects. So for we can recover a geometric stack from the quantum core, this infinite category with its T structures. So if we take the heart of this T structure, we get this abelian category, the quantum core of X heart, and this encodes the information of the T structure on the quantum core of X. So we hopefully, because this category is only related to the zero truncation of a general geometry stack, so maybe we can start from the zero truncated geometry stack. And now our statement is the R point. We only consider about the affine case. I mean, we take the Y to a affine one given by a commutative rings. Its R point is also fully faithful to these functional categories, and the essential image is also generated by some symmetric Molloy functors between the heart of respect to the corresponding the T structure, but we also need F preserves small colimits and preserve flat objects. Because now we don't mention the preservation of the collected objects, because as I said, the functor is defined on the heart of quantum core, so it encodes the information of the T structure, which is related to the connected objects. And for the third requirement, it requires F carries every exact sequence with in which each term is a flat quantum core sheaves on X, and it carries this exact sequence to exact sequence. Because in this case, in the discrete case, it's abelian categories, so we have the good notion of the exact sequence. In general, we should replace the exact sequence by the fiber sequence in the stable infinite categories. I mean, this statement is a zero truncated case, but many usually truncated trick can apply to the arbitrary truncation. It means that we may generate this theorem to the untruncated geometry stack to study some untruncated structure on quantum core. But the problem is we don't know how to describe the second and the third condition in untruncated case, because as I said, here is abelian categories. We have the good good definitions for the exact sequence and something like that. But we will, okay. So we need to know what's the meaning of the, I mean, in higher truncated case, what's the meaning of the second one and third one condition. We need to study some exact functors between the flat objects. Now, giving a geometric stack X, we use the quantum core of X flat denoted by the full subcategory generated by the flat objects. So Tannaka duality for the geometric stack told us we have if we start from the map from the Y to X, X is a geometric stack and Y is just a functor, then the pullback will give a well-defined functor from the quasi-coherent x flat to the quasi-coherent of y flat, because because it always preserves the flat objects if we start from such map. In particular, we know it preserves the fiber sequence. Also, if we have the symmetrical monoid functor between the flat object, which comes from the constant of x to constant of y, but from the exact functor from it, then it also preserves the fiber sequence. So this tells us that we can define, if we start from arbitrary symmetrical monoid functor between the flat objects. It's not necessary to require f comes from the restriction from the constant of x to constant of y. It's just given such functor, we don't know the value of f outside of the flat objects. We see if we have such symmetrical monoid functor, and if preserve the filter colimits. I think the motivation to require it preserve the filter colimits is because hopefully because in the ordinary theory of the of algebraic geometry, we know that the flat object is the filter colimits of the vector bundles or some locally free of object. So we need to f is behave well under the vector bundles between the x and y, which is somehow I think Lurie use this fact in his proof of a more general statement for the truncated Tannaka duality. And if we give such functor preserving the filter colimits, we see f is exact if it preserves the zero object and fiber sequence. It's very it's a very natural definition for exactness for such functors. because in higher categories, we should replace the exact sequence to the fiber sequence, and the preserved fiber sequence is just mean that exactness. Now there are some equivalent description for the exact functors, but we won't use them later. It's also just to preserve a good like direct sums and like good fiber sequence. Then we can show that f is exact, or it's. Now I gave our the truncated version of the Tannaka duality for arbitrary non-negative integers, because in the previous theorem is the zero truncated case of this theorem. We have this more general version of the truncated case, but be careful, but not that. If we take the untruncation of the constant core, it also has the natural symmetrical monoid infinite category structure given by taking the tensor product and then take the untruncation. This theorem also try to recover the R points of a geometric stack from the functor category between the untruncated quasi-coherent sheaves. So okay. So if we have the R is R somehow it corresponds to a affine space which is untruncated. Then we have the R point of X can fully embeds into this functional category. And also we can describe its essential image, which is generated by symmetrical monoid functors preserving the small coordinates and induce exact functors. When we restrict to the flat objects, firstly, we have the well-defined functor. It means that this functor carries the flat quasi-coherent sheaves on X to the flat R modulus. And we require this restriction is exact in the sense of these equivalent conditions. Here the functor is given by if we start from the flat quasi-coherent sheaves on X, then we take the untruncated of F, and because this functor is we only know its values on untruncated quasi-coherent sheaves, so we need to take this truncation. But if here we start from the generate geometric stack. If this geometric stack is untruncated, then we don't need to take this truncation, and it's reasonable because it means that untruncated part of the quasi-co of X can recover the untruncation of the X. Now, and we will prove this theorem by studying some restriction. I mean, we will study the restriction of functional categories like this one, or like functional categories between the quasi-co to R modular to restricting to the flat objects. There is it means that we have such more general version of the truncated Tannaka duality. This theorem is studying because if we start from the R point of X, from the original version of the Tannaka duality for geometry stack, we know it has a good description in the functional category from the quasi-co of X to the R modular. But here for the truncated version, we even take the truncation, and this theorem is to study somehow to how to describe the essential image in this restriction to the flat objects. Also, we start from the geometric stack X, and giving n can be take the natural number or even the infinity. When n is infinity, the truncation of the infinity means that we don't take the truncation. And R is untruncated in infinite rings. We consider this functional category from the quasi-co of X, but we only take the values on the connected objects and to the connected R modular, which is untruncated. And C is the first subcategory of this functional category generated by symmetrical monoid preserving the small coordinates. And also we have the well-defined funct restriction to the flat objects, which is exact. Now we can see there is a well-defined functor, because the functor in C can restrict to the flat object on X and R modulus. So this is a restriction functor. It's well defined by the construction of the C. And now this theorem claims that this restriction is also fully feasible, and we can also know what's the insertion image. It's the symmetrical moloid functor between these two categories and preserve the filter coordinates and which are exact. We will deduce our truncated version of the Tannaka duality from this general case, but the difference of these two theorems is this is drawn from the R point is from the mapping space from the spectral of R to X, and this truncated is to study if we have the restriction of the functor category to the functor category between the flat objects. But if we start from here, it always induces some functor, it induces some map to these functors it fed through the C. Also, note that our functor category is only concerned about the connective objects. If we take the stabilization, we can we can drop the Cn here, like this corollary. For geometric stack and connective infinite rings, okay, because we can take n is infinite, so we can this theorem holds for holds if we don't take any truncations. So this correlate shows that if we consider this functor category, as I see it, the R point of X will give a function from the, taking the pullback gives the functor from the R point of X to this functor categories. Now we take the E is a full subcategory generated by some good functors preserving the small coordinates, connective objects, and the flat objects. Okay, this is the essential image of the Tannaka unity for geometric stacks. It means that the R point of X, by taking the pullback, induce the equivalence between the E and the R point of X. And because the functors in E preserve the flat object, we know we have a well-defined restriction functor from the E to the functor category between the flat objects. This correlate tells us this is also fully feasible, and we can describe the essential image like those symmetrical moloid functors preserve the filter coordinates and are exact. Let's prove this correlate using this general truncated version of the Tannaka unity. It's just the point is just to take this stabilization, because here we only know what happens for the connected objects. So let's recall the stabilization of the presentable infinite categories. We use the PRL to denote the infinite category of the presentable infinite categories and whose functors preserving the coordinates. And this is the full subcategory of this guy generated by which are generated by presentable stable infinite categories. And in Lewis higher categories theories, we know this category is a reflective subcategory of this guy. It means that the including functor admits a left adjoint, which we refer it as the stabilization functors. It means that if we have a generally printable infinite category, we can get a best approximation to it, a best printable stable infinite category, which is very close to it. So therefore, somehow we know these two guys have the symmetric monoid structures. One can prove that if the underlying infinite category between them admits some adjunctions, then we can postulate the commutative algebras, which gives the theme values on the objects. So we have the homotopy equivalence between this mapping space. Here C is the arbitrary printable infinite category, and D is a stable one. So, a useful trick to deduce the equivalence of the functor category from the mapping space is replace. If we have the such homotopy equivalence, we replace D by some functor from the simplicial set K to D, and another K take different simplicial sets. Then it will induce an equivalence of this equivalence between the functor categories. Here the functor at L here means that this is a functor category generated by the symmetric monoid functors from the C to D, but I also require them preserve the small coordinates. Now, what we want to prove, we consider is from the Kaixing Cao of X to the R modulus. So we can take the C, but if we want to use this theorem, we only know what happened on the connective object. So we take C is a Kaixing Cao of X, which are connective to D. D can be taken the R modular because of the N truncation has a natural including functor to the truncation ones, to all the R modulus. But in SH, it proves that the stabilization of the Kaixing Cao of X, which consisting of connected objects, is this guy. Is all the quasi-coherent sheaves on X. So applying this equivalence, we get this equivalence. But from our construction of the E is essential. E is symmetrical monoid functors preserving the coordinates and flat objects, connected objects. So E is automatic line in the left hand side. But under this equivalence, we can identify E with a full subcategory of this functor category, which maybe we can denote it by E prime. But this equivalence somehow is obtained by taking the restrictions. So we know E is preserving the coordinates, connected objects, and the flat objects. The corresponding functors in right-hand side, the E prime is just the full subcategory of this functor category generated by those preserving the connected and flat objects. So let's return to this theorem. Here our C is defined by such functors. So I mean here E is not in this category, and the corresponding E prime is just the full subcategory described in this theorem. It's just the C, and we can conclude this corollary because it's just taking the restriction to the flat object. And this corollary is also takes the restriction to the flat objects. And we can conclude this corollary from this theorem using this identification. So we can see that as from the Tannaka duality for geometric stack, the E is just R point of X, and it gets a fully fightful embedding into the functional category between the flat objects. So it's hopeful to recover the geometric stack from the flat object of its quasi-coherent sheaves. This is a flat version of the Tannaka duality. We can prove it more generally, like we don't need to y is affine, it's arbitrary functors, but we can reduce to the affine case by the density level. This flat version shows that we can if X is a geometric stack and the y point of X is fully fightful embeds into these functional categories between the flat objects of the quasi-coherent sheaves. So in particular, this theorem tells us X can recover from the flat quasi-coherent sheaves, and also we can describe the essential image, which is just those preserve the filter coordinates and the exalt functors. The proof of this theorem is just a direct. It is immediately from the previous corollary, because although in previous corollary y is affine, but as I said, if we use the density lemma, like we can write y as a coordinate of the co-representable functors, then we can reduce to the affine case. So we may assume y is just a phi one. Now, and we can let E is a full subcategory of this guy, preserving the small coordinates, connected and flat objects. But so if we start from the R, now we assume y is affine given by R. The y point of X is just R point of X, and the Tannaka duality told us by taking the pullback, the first functor is given by equivalence of infinite categories. Now we study the second one, and the composite functor is just obtained by taking the pullback and the restriction to the flat objects. And the Tannaka duality for the geometric stack, it told us this is equivalence. And for the sixth functors, is given by the previous corollary, because E is just described in the previous corollary. It shows that the second functor is fully feasible, and the essential image is described as in the theorem, preserving the filter colimits and being exact. So now we can recover the geometric stack from the flat quasi-coherent sheaves. Okay, let's return to our truncated case. We will prove it using our a little generally truncated version of the Tannaka duality and this flat version. Okay. What we want to prove is the pullback and the retraction give this embedding theta, and we have described the essential image. So we use C denote this essential image described here. So it's a full subcategory. It's a full subcategory of this functional category on connected and untruncated objects. But from the lowest higher algebra, we know that because our target category is untruncated, we only need to study the functors on the untruncated quasi-coherent sheaves on X. So particularly from higher algebras, we know there is the equivalence of functor categories. Here, L means that we require the symmetrical monoid functor between them preserve the small colimits. And this equivalence is just induced by the including functor from the untruncated to the quasi-co of X connected. But the error is it should be the opposite. It's a restriction. So as I said, C is the first subcategory of the left hand side. Under this equivalence of infinite categories, we can identify C with the first subcategory of this guy. But by the description of the C, we know the C prime, the corresponding first subcategory in here is generated by the exact which is preserves the small colimits and induced exact functors on flat quasi-coherent sheaves. But our goal is to show X, the R point of X is equivalent to C. Now C is equivalent to C prime. So we want to show if we start R point of X by taking the pullback and some restriction, we will get the equivalence of X of R to C prime. Now because we pass to the connected part, we can use our general truncated Tannaka duality. It started some restriction of the functional categories. We know the C prime is just is a full subcategory of on the connected part, and there is a fully feasible embedding given by restriction to the flat objects, and the essential image is those preserve the filter colimits and are exact. So as I said, we start from the R point of X. We take the pullback to get a functor with target C, and C under this equivalence. C is the first subcategory of the left hand side, and we use C prime to denote the corresponding full subcategory of the right-hand side. It's a C prime. It's equivalence. Sorry, this is only C prime. And C prime has the embedding to the functional category between the flat quasi-coherent sheaves, and the essential image is denoted by this guy. So we have the two equivalence of the infinite categories, and it's a full subcategory of this functional category between the flat objects. The composite functor is just given by taking the composition of the pullback and the restriction to the flat objects. So our goal is to prove this functor is equivalence, but we have shown that the geometric stack can be recovered from the flat quasi-coherent sheaves of X. So we know the composite functor is unifizable, and the essential image is just this one. So we know that because this functor, the composite functor is unifizable with essential image C double prime, and from this we can know that the first functor is an equivalence of infinite categories, which proves our truncated version of the Tannaka duality. Now it's left our most general truncated version of the Tannaka duality is study the restriction functor from the connected part to the flat part. It's very technical. Its proof is very technical. I just gave some idea of the proof. Firstly, we can because the definition of the geometric stack shows we can find the fizable flat map from the affine space to X. We firstly treat the affine case, so we assume X is affine. And what we want to prove is from the connected part of the constant curve to restrict to the flat part will give some good equivalence. But note that the connected part is the animation of the weight bundles on X, which lies in the flat objects. But so if we know the functor, the values of the functors on flat object, and by this fact, the connected part is the animation of the weight bundles. Animation just takes some is just by taking it's a kind of the spatial. It's a spatial coordinate combination, which is very similar to the intercombination of the infinite categories. So, and we also know the F preserves all the small coordinates. So we know the values of F on flat object. We will recover the values of the F on the connected part. This proves the affine case. For the general, we will, because X is a geometric stack, we can take the unifizable map from the affine space to X. Now we can recover the flat quasi-coherent sheaves to the connected quasi-coherent sheaves on U. This is we know there is a functor related to this map, this fizable flat map. It shows that the F0 can be recovered from we can recover F0 by F0 flat. F0 flat is just the restriction to the flat objects. So we can recall, but this flat F0 is the information of it is somehow given by the F flat. So we can, if we know the F flat, we can get the F0 flat, and then in the affine case, we can recover the F0. So now, and finally, we can, because this is a 5-4 flat map, we can use some kind of technique, the 5-4 flat descent trick to prove the results on X. It just by some very I mean, it just is a very complicated progress of the 5-4 flat descent to prove the corresponding results on general X from the affine case. Okay, thank you.
Okay, thank you very much, Kaixing. Is there any question from the audience online?
So I have a general question.
Okay.
Is it audible? Hello?
Yeah, sure.
Okay, the connection. Okay. So you mentioned the fact that for n truncated categories, you have to consider the fiber sequence. So the functors should preserve fiber sequences and it should not be exact. I just want to know what is the general philosophy is behind this. Like, are those functors in that kind of category? They are like, are they left exact, or what is like the idea?
You mean you want to define some left exactness and right exactness, right?
No. So you mentioned the fact that if it's zero truncated, then they are abelian. So you can use this exactness property. Like you can define such functors to be exact at some point. And then for n truncated categories, the definition of exactness, like it takes a different form in the sense that you have to replace. You just have to ask these kind of functors on n truncated categories to preserve fiber sequences.
Yes.
And why do we have to do that? Like, what is is there some general philosophy behind it? Or? I don't know if it's clear. Question is clear. No, yeah. So in this particular slide, there's like the third point, right? Like it has to preserve exact sequences, and you mentioned for n truncated for n positive, just have to replace condition 3 by preserving this fiber sequences.
Limits. Good question. Because like I think it's motivated from the discrete case. The exact, this part exact functors on flat objects is correspond to the second and third requirements, and in this truncated version, we restrict firstly for geometry stack, we can identify the R point of X to the functor category which preserves the coordinates. Here we also need require F preserve the coordinates, and here our target category is not the functor category from the quasi-coherent of X to the R modular. We restrict to the connected part. I'm translating something. And finally, we need to preserve some flat objects, but but as you see, if we just take an arbitrary functor between, it's not reasonable. It's not reasonable if we don't put some conditions on the restricting the flat objects. Preserving flat objects just told us we have the well-defined functors. But if it comes from the R point of X, it should have some good properties. Finally, we somehow the Tannaka unity I talked today is also keep a track the what happens on the flat objects. So because these two categories have some good categorical properties, and if we start from the arbitrary symmetrical monoid functor between the flat objects, I don't think it's reasonable to recover some information of X, because although in the original version of the geometric stack we only require F preserve the we only the F give a well-defined functor between the flat object, but we don't mention it has the good property, because here we also restrict the connected part, and but the original version is the right hand side is between the whole part of not only on the connected part, but all the quasi-coherent sheaves on X, and I think this part is to provide the loss information from the non-connected part. Because this is a little different from the original version of the geometric stack. This is a quasi-co of X. Now, truncated case is connected. If we impose exact condition on flat part, I think it encodes some information on the left part of the quasi-coherent sheaves.
All right, thanks.
Okay, is there any other question? Okay, that does not seem to be the case, so we thank Kaixing again.
Thank you.
Okay, and so goodbye everyone. This was the last talk of the year, and see you hopefully in the future. Bye-bye.